Let's have a look at the exponential function. The parent graph is given by the equation y is equal to b to the power of x. We will start with b, the base, is a number that is greater than 1. If you remember from grade 10, you will recall that the base can be greater than 1, or the base can be any number between 0 and 1. Let's start with y is equal to 2 to the power of x. b is equal to 2 in this case, which is a number greater than 1. This graph represents what we call exponential growth. The asymptote is that dotted line there, the x-axis. The y-intercept can be found by putting x equal to 0, so the y-intercept is at y equal to 1. Then the domain will be all the values of x, which are real numbers. But for the range, the only y values that will work here are the y values that are greater than 0. Let's look at the graph when b is a fraction between 0 and 1. Just take note of the shape. We are using, as an example, y is equal to half to the power of x. The shape of the graph looks like this, and we call this exponential decay. The other properties will also include the asymptote. There is only one asymptote for the exponential function. The domain are all the real values of x in this case, but the range, once again, are all the values of y that are greater than 0. But in grade 11, we look at exponential functions whose equations look like this. As an example, I want us to take an example where a is a positive number and b is greater than 1. That will tell you something about the shape straight away. Because b is greater than 1, we expect our graph to show some exponential growth. So you understand the shape will look like this one here. But this graph is an asymptote, this time at y is equal to 3. So the asymptote is at y equal to 3. And you will remember that the asymptote is always related to the q value there. The asymptote is given by the equation y is equal to q, but in this case q is equal to 3, which makes the asymptote y is equal to 3. You can work out the y-intercept. Just put x is equal to 0, and that should give you the y-intercept at 4. The domain will be all the real values of x, but the range will be all the values of y that are bigger than 3. Since y is equal to 3 is the asymptote, and the graph is above that line, we know that there cannot be an x-intercept in this case. If, however, you make a negative, like in this example, I just made a negative 2. A minus sign talks about a reflection. In this case, the graph is below the asymptote, and this is because the graph is actually reflected along the horizontal asymptote. The other things to take note of could be the domain and the range, which are obvious from this graph. The domain will be all values of x, and the range will be the values of x that are smaller than 3. If, however, a is negative, but b is a fraction between 0 and 1, maybe put that 1 over 2 inside a bracket, then because of the negative sign, which is sitting there in front of 2, we know that there is a reflection in this case. And this reflection is taking place along the dotted line, which is our asymptote. If maybe the minus sign was in front of the whole function, f of x, then the reflection was going to be along the x-axis. So we need to be very careful here. This time we are just reflecting along the line y is equal to 3. If you have a good understanding of the properties of the exponential function, you can then draw these graphs with much ease. Let's see how we can use this one here. The first thing I would worry about is the shape of this graph. I notice in this example that b is equal to 1 over 2. And then remember that when b is between 0 and 1, then your graph gives you what we called exponential decay. So the graph will look like that. So I know the shape of that graph should look like that. In particular, because a is also equal to 3, which means a is positive. This tells me that the graph should be sitting somewhere above the asymptote. So that will be above the asymptote. So I know the shape. So let's find the asymptote. The asymptote is given by y is equal to q. So in this case, y is equal to 1, right? And then the intercepts, let's find the y-intercept. For the y-intercept, we need x to be equal to 0. If you substitute x equal to 0 into that function, you should get y is equal to 7. Now, when it comes to the x-intercept, you can work it out by putting y is equal to 0. But you will discover at some point that if you let y is equal to 0, you don't find a corresponding value of x. There is actually no x-intercept for this graph. Try that and see what you get. But from the previous discussion, we said our graph should be sitting somewhere above the asymptote. And our asymptote is given by y is equal to 1. So you can imagine something, this graph is sitting above y is equal to 1, which means this graph has no chance to actually intersect with the x-axis. So there's no x-intercept at all. There's no need to work it out. If you try to work it out, then you will obviously let y equal to 0. But if you do that, you get 0 is equal to 3 multiplied by half to the power of x minus 1, all that plus 1. If you move the 1 to the left and you divide by 3, you then get a negative 1/3, which is equal to half to the power of x minus 1. Once again, when you are there, you need to remember that from the parent graph of half to the power of x, we can never get a negative value for this expression. Half to the power of anything will always be positive. Now let's draw the graph. Remember the asymptote we said is given by y equals 1. And the y-intercept is at y equal to 7. And we know the shape this time. So our graph should look something like that.